Hi class. In this video we're covering section 4.2 and I've got written here the same equation that we saw at the end of the last video, our second order linear differential equation with constant coefficients. So here A, B, and C are constants. But the one thing that we have simplified here is we've made our external forces from our spring metaphor, but whatever's on the right-hand side, we've made this equal to 0. And this is what makes it called homogeneous. Homogeneous. It's a slightly different use of the term than you saw a few sections ago with the when we were doing substitutions. And if you could write the function in terms of y over x, then we call that homogeneous. This is just a different use of the term, and I can't explain why the same term is used, so don't ask me. So we saw some solutions to equations like these in the last section, and they looked like sines or cosines or exponentials. And so we're going to take a guess here. We're going to think whatever the solution here is, we need the second derivative and the first derivative and the function itself. If you add up, make like a linear combination of them where you're multiplying all of them by constants and adding them together, we need them all to cancel out in the end. So we sort of need a sine and cosine is not necessarily a good guess here, because if you started off with sine, your derivative would look like cosine, and then your second derivative would look like sine again, and the terms wouldn't cancel out if you had cosines and sines. So we're going to go back to the exponential function. Because when you take derivatives of exponential functions, they stay exponential functions, so there's a chance that things could cancel out. So we're going to guess y of t equals some exponential function e to the rt. R would be a constant here. Okay, and then we plug that in, and you'll get your second derivative would be r squared e to the rt. So we've got a r squared e to the rt plus b r e to the rt plus c e to the rt equals 0. Now, e to the rt is never 0, so we can divide by e to the rt. And so I put a implies here. This actually goes both ways. So this line is true if and only if a r squared plus b r plus c equals 0. And then that is equivalent. That's a quadratic equation, so we can use the quadratic formula. Say this thing is equal to 0 if and only if there's only two possibilities for what r could equal. R would have to equal negative b plus or minus the square root of b squared minus 4ac over 2a. So that's great. If we can just calculate this, then we can plug that in for our r up here, and we get a solution to our equation. Okay, so now a terminology thing here. This equation is called the characteristic or auxiliary equation for our ordinary differential equation H. And so that's going to come up a lot. And we know, because we know about quadratic equations, that there are three cases. three cases. So one, we could have that inside the square root here, that piece is called the discriminant. B squared minus 4ac. If this is positive, then you can take that square root, no problem, and you get two different answers because you get plus or minus that square root. And so then you end up getting two real roots. And I meant to say two distinct real roots. The second case is if b squared minus 4ac, if this exactly equals 0, then whether you do plus or minus, it doesn't matter, it only gives you one. So then you get one repeated root. And then 3, if b squared minus 4ac is negative, then you can't take the square root in the real numbers, but you get complex roots. Okay, so those are basically these three cases for solving our characteristic equation. Give you or correspond to three different cases of what kinds of solutions we have for our equation H. Okay, and that'll all depend on what your A, B, and C are. So let's consider the first case. So let's call those roots R plus, which would be negative B, plus the square root of B squared minus 4AC over 2A, and R minus equals the same thing, but with the minus up here. So then we've already shown that y1, which I'll define as e to the r plus t, it's unfortunate notation, but it's what it is, and y2 equals e to the r minus t are solutions, okay? Like that's what we just worked out, because we worked out that if r is a solution to the characteristic equation, that quadratic equation, then e to the rt is a solution to h. So solutions to h. So the question is, are there any others? And the answer is sort of obviously yes, because go back to our equation, y equals 0. So the identical 0 solution where y of t equals 0 for all t. Well, if you plug that in to h, it's obviously satisfied because your right-hand side equals 0, and you get, y double prime and y are all 0. So that's easy. So there's another solution right there. And in fact, because our equation is linear, well, let's go back and look at the equation. Because our equation is linear, if you have any two solutions, then a linear combination of those two solutions will be a solution as well. So what I mean by that is that any linear combination, let's say y of t equals c1 y1 of t plus c2 y2 of t, is also a solution to h. And if that doesn't seem obvious to you, I recommend that you try plugging this combination into h And when you take your derivatives, you'll see that because the derivative, taking a derivative is also linear. So it, like, you can break it apart and pull out those constants and pull apart the addition. And then you get something with y1s in it, you know, a1, y1, double prime, blah, 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 blah. That stuff equals 0. And then the same thing with y2, that stuff equals 0, and you add them together and you get 0. Okay? So what this suggests is that you remember with our first order equations, we usually had a constant in it, and we solved that giving with our initial condition. And this suggests that we might need, because we have two constants, we might need two initial conditions in order to solve it. So think about a really easy case. Of y double prime equals 0. So we know how to solve that. We don't have to use the roots or anything like that. But we know that y prime equals c1. We can just antiderivative that, and then y would have to equal c1t plus c2, right? And obviously, if y double prime equals 0, that's a straight line. Okay, so this is our solution, y of t, and it's determined by 2 points. Okay, so by either 2 points or a point y at some t naught, and the slope, which is just the derivative. So if you have a point on it and you have a point on the derivative, that is enough to solve for this in this case. And that's what our sort of initial values end up looking like for these problems, where you have not just an initial point, but an initial first derivative as well. So let's do an example. We have an initial value problem, y double prime plus 2y minus y equals 0. And y, we're given our initial points, y at 0 equals 0, and y prime at 0 equals -1. So how do we solve this? The characteristic equation is r squared plus 2r minus 1 equals 0. And then the roots are r plus equals -1 plus square root of 2, and r minus equals -1 minus square root of 2. So then our solutions look like y of t equals c1 e to the -1 plus square root of 2 t plus c2 e to the -1 minus square root of 2 t. So next we will plug in initial conditions. So the first one, y of 0 equals 0, is going to give us e to the 0 is 1, so we just get c1 plus c2 equals 0. And then y prime at 0 equals -1. Well, if we take y prime, then the coefficient up there in the exponent comes down to the front, and we still end up with the exponential part going away. So we get -1 plus square root of 2 c1 plus -1 minus square root of 2 C2. And we can simplify this a little bit. We get negative C1 plus C2 plus square root of 2 times C1 minus C2, and that's equal to -1. And of course, so now we have to solve these two together. And so we can take C1 plus C2 equals 0, and that goes away. And then we can plug in that C2 equals negative C1. So in the end, we solve this all together and we get C1 equals negative square root of 2 over 4, and C2 equals positive square root of 2 over 4. So then that gives us our solution. Y of t equals negative square root of 2 over 4, e to the -1 plus square root of 2t plus square root of 2 over 4 e to the -1 minus square root of 2t. Okay, so that's how we do these initial value problems in this case. So at least in this one case, we've shown how to find a solution. And in fact, we have a nice theorem that gives us existence and uniqueness of solutions for this type of equation. So I'm going to write that out right now. So for proof, we're not actually going to prove it, but we've started to prove the existence. We showed the existence of a solution in the two real root cases already. And then we'll show in other cases coming up soon. The fact that it's unique, we haven't shown, and that's really outside of the scope of the class. So what we are going to do is prove a theorem that tells us that the way that we solved an initial value problem before, missed it, is always going to work. Okay, so what we did before is we had this initial value problem here, and we found two solutions. We found our roots, and we found these two solutions, and then we put constants in front of them, and then figured out what the constants would need to be to solve that initial value problem. So the question is that always going to work, or when is it going to work, or are there other methods that we can use to solve our problems? And that's what our next result is going to give us. So we'll start off with a definition. A pair of functions, y1 and y2, are said to be linearly independent on a given interval I. So I is an interval of t values. They are linearly independent if and only if neither of them is a constant multiple of the other on all of I. So some examples on, let's see, on 0 to 10, y1 equals x and y2 equals 10x are not linearly independent because, of course, one is a constant multiple of the other. And on the same interval, y1 equals x and y2 equals x squared are linearly independent. This might seem like sort of a weird definition, like why do you need a term to why don't you just say that, I don't know, one's not a constant multiple of the other? Linear independence has can be generalized to more than two functions, but then the definition gets a little bit more complicated. And for right now, we only need the definition for two functions, and it really just comes down to being constant multiple. So anyway, next I'm going to state the theorem, so I'll write it out. So I've brought down two of the problem statements that we have seen earlier. So H is our homogeneous equation, which doesn't have any initial conditions with it. It's just the equation. And then IVP is what I'm calling our initial value problem, which I pulled from the last theorem. And that's H, but with initial conditions on one initial condition on Y and one initial condition on Y prime. Okay, so now the theorem states that if Y1 and Y2 are any two solutions to H, which are linearly independent on all the real numbers, then you can always find unique constants C1 and C2 so that this linear combination C1Y1 plus C2Y2 satisfies the initial value problem. So this is just saying that the approach that we took, where we found our R's and we found um, our two solutions, e to the R1t and e to the R2t, or I guess we used e to the R plus t and e to the R minus t. Those two solutions were linearly independent, of course. I mean, you can sort of think that out yourself. And then we said, well, then the solution to the initial value problem must be this linear combination here. And let's solve for the constants for the C1 and the C2. And what this theorem is saying is that that method is always going to work. And so let's prove out why. So we know that this y that we've defined is a solution to H, to just the equation by itself, because if y1 and y2 are solutions, then any linear combination is going to be a solution. We talked about that earlier. So we just need to show, it is really hard to talk and write at the same time. So we just need to show that we are going to be able to find those C1 and C2 such that we can plug in. And so if we plug in our initial conditions, we get y of t naught equals C1 y1 t naught plus C2 y2 of t naught. And we need this to equal big Y naught. And then our y prime of t naught is going to be equal to C1 y1 prime t naught plus C2 y2 prime of t naught. And that needs to equal big Y1, big Y1. And so again, this is exactly what we did before. We plugged in our initial conditions and then we had to do some algebra to solve. Okay, so algebra, we can do this in the sort of general case here. And we can get our solutions, make a little room. C1 equals, well, let's just write. So we can actually do the algebra out and get exactly how to solve for these constants C1 and C2. So, we're done. We have shown that we can already solve our C1 and C2. However, there's one problem, and that is this right here. So we need this to be non-zero. And these are the same on both terms, you'll notice. We need this to not equal 0. So we can show then a little lemma. A lemma is like a helper theorem. So our lemma states that if y1 and y2 are linearly independent functions, then for any t naught in the interval where the functions are linearly independent, then this quantity y1 evaluated at t naught times y2 prime evaluated at t naught minus y1 prime t naught, y2 of t naught, that quantity is always non-zero. And so our proof, let's see, proof by contradiction So proving by contradiction means that we're going to suppose that there actually is some t naught where that quantity equals 0. Okay, and so we're going to show that that gives us some sort of problem. And so there's a couple different cases here. We're just going to do one, case one. So let's suppose y1 of t naught, that particular part of it is not 0. And we're going to define this kappa to be the quantity y2 of t naught over y1 of t naught. So you see why we assumed y1 of t naught was non-zero, so that we could define this ratio. So then we can say that the function, we're going to make a new function, z of t, just z of t, which we're going to define to be this constant kappa. It's a constant because we've plugged in t naught into these functions, and so it's just a fixed value. So kappa times y1 of t is a constant multiple of y1. And so it's a solution to our homogeneous equation, okay? Because y1 is a solution to h, and because it's got 0 on the right-hand side, any constant multiple, in fact, any linear accommodation of solutions is also a solution, okay? So also, we want to think about how z satisfies the initial conditions of our initial value problem. So if we plug in also z at t naught, if we plug in that initial point, that's going to be kappa, which is y2 of t naught over y1 of t naught, times y1 of t naught, which equals y2 of t naught, okay? And let's think about our other initial condition, z prime. So z prime would be just kappa times y1 prime. So we get our kappa, y2 of t naught over y1 of t naught, times y1 prime of t naught. And that equals y2 prime of t naught because of this equality right here. If you add this to the other side, to the right-hand side, and then divide by y1, you get exactly this quantity right here, this equation. And so what that then tells you is that z of t is a solution to the initial value problem that has these initial conditions. So I'll write that. So remember, we assumed before that y1 and y2, and then by extension z, are solutions to h, which is just that equation. And those functions themselves might have different initial conditions. But we've shown that the initial conditions for z are these two numbers here, which are also the same initial conditions for y2. So because we already saw that this initial value problem has a unique solution, we didn't prove it, but we stated it, which was going to be good enough. That means that z and y2 have to be the same function. So again, since this initial value problem right here, it has a unique solution by the theorem we stated before, and we've obviously y2 is the solution to it, and we've shown that z2 is the solution to it. So that then it follows that z2 has to equal y2, okay? But z of t is kappa times y1. So then it follows that y1, let's see, say it this way, y2 is a constant multiple of y1. And that is a contradiction. That's the symbol we sometimes write for contradiction. Because we assumed that y1 and y2 are linearly independent. So we got a contradiction. So the assumption we made up here can't be true, at least for this case. So the other cases where y1 of t naught is not equal to 0, you can assume a different point. You can kind of flip it around and do it the other way, which I'm not going to do here. So let me say that the other cases similarly will lead to a contradiction, and you can see the details of that in the text. And so what we conclude then is that there can't be a t where that quantity equals 0. So we conclude then for all t naught, our quantity y1 of t naught, y2 prime of t naught minus y1 prime of t naught, y2 prime of t naught is not equal to 0. And so we're done. We can always find our c's and get our solution. So this is nice. I know this was a lot of theory and a lot of proof, but the point is that we now know that whenever we want to solve an initial value problem, what we need to do is find two linearly independent solutions and to the homogeneous equation. And then we can always solve for our constants that will give us the particular solution for our initial value problem. So to write that out again, in order to find the solution to our initial value problem, first you find two linearly independent solutions to H, the homogeneous equation, and then you plug in your initial conditions and you solve for your constants C1 and C2. All right, so I know this video is getting long, and we're not done yet, because this is, I'll say here that this chapter is really sort of very foundational, or this section in particular. So I think it's important to go through the theory of why this method is always going to work, because we're going to be using it over and over again in the next chapter and really beyond. So we're going to go back to what we were doing before. We used, remember, we had a homogeneous equation, and we used the characteristic equation from it and solved for the two roots, and then we got two linearly independent solutions. But we know that there's another case where if your discriminant equals 0, then you're going to get only one solution to the quadratic equation. And so we need to figure out how to get a second linearly independent solution. So I'm going to do an example here. So here's our example problem. If we plug in the characteristic equation, the quadratic formula here, we get that r equals -2 is a double root. So that tells us that we've got at least one solution to the homogeneous equation. So y1 of t equals e to the -2t is one solution to, I'll say just to h, which just refers to the equation part, but doesn't include the initial conditions. And so what's another one? Well, another one is y2 of t equals t e to the -2t. Okay, and I'll let you verify that And you can also verify that y1 and y2 are linearly independent. And so the general solution is y of t equals c1 e to the negative 2t plus c2t e to the negative 2t. And if you plug in the initial conditions, you end up getting c1 equals 1 and c2 equals 5. So then your final answer, your final solution will be y of t equals e to the negative 2t plus 5t e to the negative 2t. So that worked. I mean, I didn't give you any sort of motivation for how I got that t e to the negative 2t, but you can show that it always works. So more generally, let's plug that solution in, that y equals t e to the rt. And if we plug that into our equation, we get, you've got to do product rule a couple times, and you get a bunch of terms that have e to the rt, t e to the rt. So you can work out those details and separate things out. And so in order, we want this to equal 0. And so we want both things in the brackets to equal 0. So this one equals 0 because r is the root of the characteristic equation. We've got, that's the characteristic equation right there. Now, this first bracket term here is also equal to 0 because r is a double root. Because what we have there is that from the quadratic formula, r equals negative b plus or minus the square root of b squared minus 4ac over 2a. But that term in the square root is 0, which is exactly why we got a double root. So that's just negative b over 2a. And so if you move everything to one side, you get 2ar plus b equals 0. Okay, so that tells us that this whole quantity equals 0, so that means that our y equals t to e to the rt is a solution to our equation if r is a double root. Okay, so that tells us that in our case where there's a repeated root or a double root, the general solution looks like y equals c1 e to the rt plus c2 t e to the rt. Okay, so there's one more case, which is where you've got complex roots, and we're going to do that in the next section. So that pretty much wraps up this section here, and we'll see a lot more cases in the coming section of how you use more general cases of this type of equation. All right, see you then. Whoops.